friends. We'll do numerical problems based on packing in unit cells. If you remember what we studied, if you take SCC, rank is 1, a relation between A and R is A is equal to 2R. If you remember, in SCC, spheres were touching each other along edge length. Packing fraction was pi by 6. Remember this pi by 6 also. Remember 0.52 also. Both the numbers are important from MCQ perspective. And if you remember for BCC, along body diagonal, you remember body diagonal? Body diagonal, A root 3 was equal to 4R. Rank was 2. And we have to remember both pi root 3 by 8, that was packing fraction, exact value is 0.68. For FCC, along face diagonal, the spheres were touching each other and therefore 4R was equal to A root 2. Rank is 4 and this value also we are supposed to remember pi root 2 by 6. Packing fraction is 0.74. All these numbers have to be remembered and they are important for all the examinations. So, which of them is most efficiently packed? FCC. And which is least packed? Simple cubic crystal. So, least packed, max or most dense packed. So, most efficient packing is for FCC. We go to one numerical where this data is given. Now, what is 361? You should all know its edge length and symbol is A. There are 4 atoms making up unit cell. What does this means? It means rank is 4. You know, when rank is 4, it is called as FCC. It's called as FCC. So, 361 is edge length and 4 atoms, number of atoms making up unit cell is 4. Z value 4 means it is FCC. For FCC, what is the relation between R and A? 4R is equal to A root 2. So, what is the value of R? R value is A root 2 divided by 4. Put the value of root 2, 1.414 upon 4. If you are doing it for board exam, use log calculations. Otherwise, for MCQ exam, do an approximation and the value is 127 picometer because the original data was also in picometer. That was a numerical to get a relation between A and R. We go to another numerical. Another numerical that we have is, right, we have a cubic solid made up of 2 elements, P and Q. Now, what are such type of solids which can be made up of 2 elements? They can be ionic solids like NaCl, Al2O3, or they can be alloys. Anyone who is made up of 2 or more elements can be an alloy or can be an ionic solid. Now, they are asking what is the formula of the compound? How to do it? Let the formula of the compound will be Px Qy, where X is a number of P atoms and Y is a number of Q atoms. So, Q are present at the corners. If anything which is present at the corners, you know each corner contributes 1/8. Each corner contributes 1/8 and there are 8 corners. So, number of Q atoms are 1. That means Y value is 1. Y value is 1. 8 is number of 8 corners. 1 by 8 is contribution and therefore, the Y value is 1. We go to next. P. To know more about P, we go to the next. P is present at body center. How many body centers are present? 1. What is the contribution of each body center? Yes, 1. So, number of atoms of P are 1 is number of spheres at body center, contribution is 1. So, total number of P atoms are 1 and X value is 1. If you remember how to write a formula, we remember it was Px Qy and the value of X is 1 and value of Y on the previous slide was 1. Therefore, the formula is PQ. Coming to the next one. Solid has cubic structure in which X atoms make up corners, Y atom makes up cube centers, and oxygen atom makes up edge center. What is the formula of such compound? Again, what type of compound they can be? This type of compound can be ionic compounds. Ionic compound. Can there be ionic compound made up of 3 elements? Yes. Na2SO4, it is made up of 3 elements. Sodium, sulfur and oxygen, or they can be alloy. So remember, such type of compounds can be ionic compounds or they can be alloy. So coming to the discussion, let the formula of the compound be XaYb and OC, where A stands for number of X atoms, B stands for number of Y atoms, and C stands for number of oxygen atoms. You have to calculate only the value of A, B and C. Right, X makes up the corners. If you say it makes up the corners, each corner contributes 1/8. So 8 multiplied by 1/8, so it is 1. So from this, what you came to know, the value of A is 1. So we got the value of A. Now we are left with only value of B and C. We go to the next part. Where are Y atoms present? Cube centers. How many cube centers are present? How many cube centers are present? Number of cube centers are 1. And contribution is 1, therefore value of B is 1. Similarly, if you go to oxygen atoms, oxygen atom makes up edge centers. And how many edge centers are present? Edge centers are 12. Each edge center contributes 1/4. So total is 3. So value of C is 3. So formula is XaYb OC. If you put that XYO3, this is what is the formula that you get. If you want to again see, X atoms makes up corners. Corners means 8 multiplied by 1/8, that is 1. So X ka value is 1. Y makes up cube centers. Cube centers are 1. Each contribution 1. Therefore, value is 1. So Y is 1. So X is 1. Y is 1. And oxygen makes up edge center. How many edges are there? 12. Each edge center 1/4. Therefore, 3. So oxygen is 3. Therefore, formula is X1 Y1 O3. So we come to the end of the numericals connected to this part. We will continue with density in the next class. Student friends, so we come to the next part of the chapter solid state, and we come to important part of a solid state, packing in solids. In today's session, we will learn one dimensional, two dimensional, and when this topic is going on, right, be aware of the term coordination number and voids. Try to understand them properly. So we go ahead. One dimensional. Now we have to imagine metallic atoms as a spheres. So what we are trying to show is how these metallic atoms, which we call it as spheres, can be arranged. Metallic atoms, we are visualizing them as a spheres, and you should know, for a given metal, all the atoms are of the same size. All the atoms are of the same size. So here all the right spheres will be shown of the same size. Now this type of an arrangement along x axis is called as one dimensional. You can have one dimensional arrangement along y axis also, and we can have one dimensional arrangement along z axis too. This is what is an arrangement all about. Linear arrangement or one dimensional arrangement. So if you check one dimensional arrangement along x axis, now you have to imagine infinite number of spheres. If you imagine infinite number of spheres, always keep it in mind, we show a finite arrangement here on the board, but you should imagine infinite number of arrangements. If you take one of the sphere in that arrangement, which has been made blue in this case, then this sphere we call it as a desired sphere. It is in direct contact with how many other spheres? It is in direct contact with two other spheres. Remember, this sphere is not in direct contact with the desired sphere. This sphere is not in direct contact with desired sphere. It is in direct contact with only two sphere, which I have labeled as 1 and 2. If it is in direct contact with only two sphere, then such a thing is called as coordination number. What is a coordination number? The given sphere is in direct contact with how many other spheres? When I say the word direct contact, remember there should be a touch. The sphere should be touching the other spheres. That is called as coordination number. Now we go to two-dimensional arrangement. If you see two-dimensional arrangement, then what you will realize, there is another set of spheres coming up. Now that means along xy axis. If you go on doing that arrangement, this is two-dimensional arrangement. This is simplest two-dimensional arrangement that we can visualize of. Simplest. Now what you are able to realize, the exactly on the top part of it, another top is also arranged. On the top part of it, another top is arranged. Remember this type of an arrangement. Right, every one dimensional layer is stacked above each other. In this case, coordination number is 4. If you take desired sphere D, it is in direct contact with how many other spheres? It is in direct contact with only 4 other spheres. Sphere number 1, sphere number 2, sphere number 3 and sphere number 4. It is in direct contact with this. Remember, this sphere, it is in not direct contact with D sphere. Even this sphere is not in direct contact with D sphere. Even this sphere is in not direct contact with D sphere. Even this sphere is not in direct contact with D sphere. So it is in direct contact with only 4 spheres. Therefore, coordination number is 4. If you check the entire arrangement, what do you realize? The arrangement is of the same type. Such type of arrangement is called as AA type of an arrangement. If you label this row or this layer as A, then this layer also should be called as A, because it is exactly of the same type. Even this should be called as of the A type. Such a type of arrangement is called as A type of planar arrangement. There is one more name for this before that. The void space, empty space, which we in a common language call it as hole, in a scientific language is called as a void, and the void is square shaped. Square shaped void. For your information, that void has a comparable size to that of the sphere. Coming to more discussion in this case, if you know that this sphere was in direct contact with this sphere, it was in direct contact with this sphere, it was in direct contact with this sphere, it was in direct contact with this sphere. If you take the centers of the 4 spheres which was in direct contact with the blue color sphere, then the shape that you get is called as square, and it is called as square close packing. The word close, that means spheres are touching each other in all the layers. Square close packing. And remember, coordination number was 4. Now, two-dimensional, another possible arrangement which we can think from mathematics point of view. Now, if you remember in the previous, on this top there was another sphere. Now, what is another possibility? Now, on this top you do not have a sphere, but in the gap you have a sphere. In the gap, if you have a sphere, this is another type of an arrangement that you can have. This is more efficient type of an arrangement that we can think of. More efficient type of an arrangement. If you take a blue sphere, which is a desired sphere, it is in direct contact with how many other spheres? It is in direct contact with 6 spheres. That means its coordination number is 6. Remember, higher coordination number. Remember, higher coordination number means better, or you can call it as efficient packing. Efficient packing. Remember that. Now, what is such type of packing also known as? You are able to see the arrangement is not right, different types. Such a type of packing is called as AB packing. The layer in which this is not exactly the same, it is quite different, but you are able to see this and this is exactly the same. This and this is exactly this, a pattern of the arrangement, while this and this is exactly same. So, such a type of arrangement is called as AB type planar arrangement, and the coordination number, if you remember, it was how much? 6. If you take the blue colored sphere and you try to find out a shape, the hole in it is triangular shaped, and the size of the hole is smaller as compared to the previous packing. Remember? Now, if you try to think more and understand, what you will be able to get. If you take this sphere number 1, sphere number 2, sphere number 3, sphere number 4, sphere number 5 and 6 and you take their centers and you join them, then whatever red shape that you get is called as hexagon and it's called as hexagonal close packing. Now, if you remember, this is AB packing and this what we learned previously was AAA packing. If you want to say AB close packing, that is another name for hexagonal close packing. This is called as AAA close packing, also called as square close packing. Remember, we are learning two dimensional. So, if you want, you can add the word planar. If you want, you can add the word planar so that you don't get confused. Coordination number in this case was how much? Coordination number in this case was 4. Coordination number in this case is how much? 6. Now, if you try to understand how many holes are there, if you count the number of holes in this entire packing, then you will get 16 holes or 16 voids. Similarly, if you try to count the number of holes in this, if you count the number of holes in it and you go on, you will find it is 32. So, 32 voids, that means number of voids in hexagonal close packing two dimensional is double of square close packing. So, number of holes are double in HCP. So, that was the end of two dimensional packing. Three dimensional packing we will be learning in the next class. Hello student friends, we come to packing in solid state in three dimensional, where we will be learning about SCC arrangement, hexagonal close packing, that is called as HCP arrangement, cubic close packing, which is also known as FCC arrangement. Whenever this topic is going on, give importance to coordination number and understanding voids. Three dimensional arrangement, if you see, check. This is a three dimensional, it is a two dimensional. Now, we are trying to place spheres above each other. If you place the spheres, how they can be placed? Now, we have started three dimensional arrangement. Now, always remember, whenever you talk about such type of arrangement, imagine infinite number of spheres in all the directions. Again, if you have forgotten, remember, all these are metallic atoms, which we are considering them as a spheres and they are of the same sizes for a given atom. Now, such a type of arrangement is called as AA type of arrangement, right. Whenever we say such type of arrangement, we generally use 4 times the same letter. So, A type of an arrangement, so that to avoid any type of a confusion. This is A type of an arrangement. Now, if you check how it looks, the simplest one, if you have remembered the word brick and the wall, we have come to a brick, a small unit cell. A small unit cell will be made up of 8 spheres. Such a type of packing is called as square close packing. If you remember, square close packing, or you can say simple cubic close packing. Simple cubic close packing, where 8 spheres are making a small unit cell, if you remember. So, simple cubic close packing. Now, if you remember, this is brick. If you remember, unit cell is called as a brick and this is called as space lattice. If you want to know, space lattice is nothing but for us wall. If this is wall, this is the brick, and brick for us is unit cell. And what is the name of unit cell? SCC. And the wall that you get is called as A type of an arrangement. So, we say brick is SCC and wall is A type of a backing. This is what we understand. And if you remember, what is a gap inside? What is a gap inside called as? The gap inside is called as cubic void. The gap inside is called as cubic void. Gap inside is called as cubic void. Remember that. What is the coordination number for SCC or A type of an arrangement? Whether you say SCC or AA type of arrangement, for us one and the same, because one of them is a unit cell and other is a space lattice. The coordination number for both of them will be same. If you try to find out coordination number, then if you take this as a desired sphere, it is in direct contact with how many spheres? It is in direct contact with how many spheres? It is in direct contact with 6 spheres. What is the coordination number? Coordination number in the previous case is 6. So, we say whether you say SCC or A type of an arrangement, coordination number is 6. This is the simplest possibility of a 3-dimensional arrangement which will have coordination number of 6 and void present will be cubic void. Name SCC as a brick or a unit cell and as a space lattice is known as A type of an arrangement. We go to another type of an arrangement, 3-dimensional arrangement. Now, this is quite different, and if you remember, we have already learned under the 2-dimensional discussion. Now, what if you remember, what is this type of an arrangement called as? Such a type of arrangement is called as AB type of an arrangement. AB type of an arrangement. What we have done is we have taken out unit cell out of it. This is how it will look from the top, this is how it will look from sideways, and if you try to check, this type of an arrangement is called as which type of an arrangement? AB type of an arrangement, AB type of an arrangement. Now, we come to AB type of arrangement, 3-dimensional. Now, if you take out this layer, then it will look like this. This layer it will look like this, and this layer will look like this. If you take this as a desired sphere, it is in direct contact with how many spheres? It is in direct contact with 6 spheres. It is in direct contact with 6 spheres in a layer. As in direct contact with 6 spheres in one layer. In one layer, 6 spheres. And it is in direct contact with how many spheres? 7, 8, 9, 3 above and 3 below. So, it is in direct contact with 12 spheres. So, this sphere is in direct contact with 12 spheres. Actually, any sphere, if you try to see in this AB arrangement, will be in direct contact with 12 spheres, 6 spheres in one layer, 3 above and 3 below. Such a type, you are able to see 6 in one layer, 3 above and 3 below. Then such a type of arrangement is called as AB type of an arrangement, and coordination number is 12. So, what is the name of unit cell? The name of unit cell is hexagonal close packing, and the space lattice is known as AB 3-dimensional packing. HCP, hexagonal close packing, where in the upper layer, one layer, how many spheres are present? Not spheres, 7 atoms are present, 1 center and 6 corners. And how many are present here? 3. We can call them as body center because they are inside the body. And this, in this layer, you can call this as first layer, you can call this as second layer, and this you can call it as a third layer. There are how many atoms again? 7 atoms. So, somebody wants to know lattice points. How many lattice points are present? Lattice points are 7, 7 and 3. 17 lattice points are present, making them an HCP. Hexagonal close packing is a name for it. Now, if you want to see, these are the two diagrams that we have drawn right to show. Now, this is new type ABC type of an arrangement, ABC type of an arrangement, ABC type of an arrangement. Now, if you see how this layer is arranged and this layer is arranged, it is different type. It is a different type. While if you see this layer and this layer, are you able to see it same type? This type of unpacking, the other side, this type of unpacking, the other type, this A, B, C, A type of unpacking, this is A, B type of unpacking, two different type of unpacking. We can remember this as above, if we call this as symbol since, and this middle layer like as if it is a flower, then this is therefore. So, we call it as like a since, flower and therefore. If you call this as since and the middle layer, this layer as flower, flower like, then this is also since. So, you can call it as since, flower, since. If you call this instead of since, somebody calls this as therefore, reverse therefore, somebody calls like this, then this also instead of since will be called as therefore. So, you can call it as since, flower, therefore, you can call it as since, flower, since, or you can call it as therefore, flower, therefore. Now, if you check, this is how it looks. Coordination number is 12. We have done it before. It is called as this type of an ABC, A type of unpacking. This is mistake. A type of packing is cubic close packing called as CCP, while the other one is called as AB packing. AB packing, and it is also called as hexagonal close packing. Here also coordination number is 12. So, both of them have coordination number 12. So, both of them are equally efficient. Remember, both of them are equally efficient, but they are different. Are you able to see this entire thing? It looks like since, this look like therefore. So, we call it as since, flower, therefore. It looks like flower, as if there is a flower, right, arrangement. You remember how flowers, if you want to draw in school, it looks like this. So, as if you are trying to show a flower, while this is since, this is flower, and this is again since. Are you understanding it? This type of an arrangement. So, we will stop here only, we will continue the next. We will try to learn how come ABCA type of an arrangement is called as a cubic close packing, which you will be knowing it is also called as face centered cubic packing. Now, what has been done is only the required number of spheres have been taken from ABCA packing and they have been labeled. If you label this as sphere number 1, then this sphere has been shown here. Sphere number 2, if you check, has been shown here. It is exactly below sphere number 1. Sphere number 3 and sphere number 4 are in one line to each other. Sphere number 3 and sphere number 4 are in one line to each other. Are you able to see this? And in between is a sphere number 2. 5, 6 and 7 are also in one line. 5, 6 and 7 are also in one line. If you are able to see this, in one line. Then exactly below 5 is 8. Exactly below 5 is 8. Exactly below 6 is 9. Exactly below 6 is 9. Exactly below 7 is 10. 10. Between 8 and 9 is 11. Between 8 and 9 is 11. Between 9 and 10 is 12. 12. Exactly between 11 and 12 is 13 and it is exactly below 9. Remember that. So, 13 is between 11 and 12 and it is exactly below 9. Are you able to see this? And exactly below 13 is 14. Now, if you see all the diagram, you will realize it is face centered cubic set. If you check sphere number 1, visualize 1, visualize 2, visualize 10. Sphere number 1, 2, 10 and 7 in the diagram. So, if you visualize 1, 2, 7 and 10, as you will get a face where 4 is a face center. If you visualize 13, 14, 10 and 7, you will get another face where 12 is a face center. Similar visualization will give rise to FCC, that is, we call it as CCP. So FCC type of an arrangement is nothing but CC type of an arrangement. If you count the lattice point, that means how many spheres are there in it? Lattice points are 14. And if you remember from the previous lecture, rank is 4. If you want to go back and check, then remember AB type of arrangement. AB type of an arrangement gives rise to HCP, where lattice points are 17. Rank from the previous session 6. ABCA type of an arrangement gave rise to CCP, which is also called as FCC, where lattice point is 14 and rank is 4. If you want to still go ahead and learn, AA type of an arrangement is SCC, where lattice point is 8 and rank is 1. So here we have concluded how come ABCA packing, is nothing but CCP or FCC with lattice points of 14. That's what we have concluded in this small video. So if you check, this is body centered cubic system animation. The blue color balls are A layer and the red color balls are B layers. Why the red color balls are called as B layers? Because they are not similar in the arrangement like A color balls. I repeat, blue color spheres are A and the red color spheres are B. Right, this is an animation for body centered cubic structure. Now if you see blue colored spheres in layers, they are not touching each other. Similarly, if you check red colored spheres, they are also not actually touching each other. I repeat, blue colored spheres don't touch each other. Even red colored spheres don't touch each other. So such a type of packing is called as AB loose packing. AB loose packing. That's the name for such type of a packing. I repeat, A and blue color balls don't touch each other. That's A layer don't touch each other. Therefore, it is the word used called as loose packing. Now, if you see a right color diagram, what you will realize, a red color sphere touches 8 other blue color spheres. Therefore, coordination number is 8. Coordination number is 8. If you see the diagram, right side diagram, you will find red color sphere touching 8 other blue color spheres. Therefore, coordination number is 8. Same if you try to visualize here on the left side diagram, you will realize a red color sphere will be touching 8 other blue color spheres. So, conclusion is body centered cubic system is AB loose packing with coordination number of 8. So, if you see a simple cubic unit cell, there are 8 spheres making up a simple cubic unit cell. If you check the bottommost layer, 2 spheres touch each other. If you see sidewise left, 2 spheres touch each other. Sidewise right, they touch each other. But diagonally opposite spheres don't touch each other in a simple cubic unit cell. If you cut a simple cubic unit cell in a proper manner, you will get a cube, a perfect cube, where each sphere now contributes 1/8. Now, if you arrange all these things, then whatever arrangement that you get is called as AAA type of an arrangement. This is a small unit cell and you are able to see a cube in it with a cubic void inside. If all the spheres contribution is checked in a cube, then you will come to know it is made up of only one sphere. That means one unit SCC cell is made up of only one sphere. So, rank is 1. Now, if you see AAA packing, which makes up SCC, then any sphere is surrounded by only 6 spheres. Right, one on the top, one at the bottom, one left, right, north and south. That means right 2 spheres diagonally opposite to each other in all directions. So, coordination number is 6 for SCC. Simple cubic unit cell, and this packing that you are able to see, or a space lattice that you are able to see, is called as A type space packing. Now if you check again a simple cubic unit cell, you will realize it is made up of 8 lattice points, that is 8 spheres make up one cube. Okay, lattice points are 8. Rank is 1, remember this. Spheres, do they touch each other? Answer is yes, they touch each other, but only sideways, not diagonally. Diagonally, they don't touch each other. If you cut in a proper manner, then this 8 spheres make up a cube, where now each sphere contributes only 1/8. And if you arrange all of this, then whatever you will get is called as A type of a packing, which has cubic void in it. So the void inside is cubic void in it. This is SCC, and if you try to count all the spheres contribution, you will come to know it makes up only 1. So rank is 1, lattice points are 8, so Z ka value is 1. This is what it is. Now if you imagine the same SCC in A type of space lattice and take any one sphere, then one sphere is in contact with 6 other spheres. Okay, so coordination number is 6. If you see, a body centered cubic unit cell is made up of 8 spheres in the corners and one pink sphere shown here at the body center. So coordination number is 8. If you remember, body centered cubic unit cell, it has AB loose packing. If you cut into a cube, it appears to be like this. And if you happen to add all the parts, then you will realize it is made up of only 2 spheres. That means rank is 2. So for BCC, rank is 2. Now if you want to see a coordination number, then please pay attention to that blue color red sphere which is at the center and pink color spheres which are at the corners. So coordination number is 8. So coordination number for body centered cubic unit cell is 8. You can see the coordination number even in this diagram. If you happen to see, then you will find a pink color ball surrounded by 8 blue colored balls. Coordination number is 8. So we end here only. Thank you all of you. What you are able to see, a face centered cubic unit cell where there are 8 spheres at the corners and 6 yellow spheres which are making a face center. So if you remember, its coordination number is 12. Now if you happen to cut it in the form of a cube, it looks like this. This is what is its structure. And if you happen to add all the parts of the spheres, then you will find rank is 4. So rank for FCC unit cell is 4, which is also called as CCP cubic unit cell. Now if you check here, you will realize its coordination number is 12. See the blue color ball, 4 spheres are in the same plane of the blue color ball, 4 spheres above and 4 spheres at the bottom. If you check again the lighted blue color ball, there are 4 spheres in the same plane of the blue color ball. Then 4 spheres which are lighted yellow are above that, and 4 spheres below that blue color ball which are not lighted, makes up coordination number 12. Now this is seeing FCC from a different 3-dimensional perspective. Coordination number of FCC is 12. First imagine the middle layer with a blue color lighted sphere and 4 yellow lighted sphere in the middle layer. So blue color sphere is surrounded by 4 spheres in that same plane, 4 spheres above which are also lighted, and 4 spheres which are below that blue color sphere which are not lighted, makes up coordination number of 12. So that was all about discussion of FCC perspective. So we end here. We come to the next topic of different types of voids: trigonal void, tetrahedral void, octahedral void and cubic void. Now this all voids are present in different types of packing which are present, like AAA packing, AB packing, ABCA packing. In all these different packings, different types of voids present are this many. When you learn voids, remember to understand the position of the void, their coordination number and how many voids are present per sphere of packing. So, first void we like to understand. The first void is, now before we understand, you should know the best packing or the most efficient packing is CCP, also called as FCC or HCP, and they have 74% of the space occupied. That means 26% of the space is empty. Empty space is also called as voids. Now, size of the void can be best expressed by a term called as radius ratio, where small r stands for radius of a sphere that will exactly fit into the void. Capital R is a radius of the surrounding sphere which makes up that void. Now, there are various types of voids depending upon their size and number of the spheres. We are going to learn first void, trigonal void. Trigonal void is a void present between three spheres. If you are able to see, we have drawn a small sphere exactly fitting into a trigonal void. Now, if you join the three spheres surrounding the trigonal void, you will actually get an equilateral triangle. Now, the trigonal void, which has been shown by a small sphere at the center, that trigonal void is surrounded by how many spheres? It is surrounded by three spheres. Therefore, coordination number of trigonal void is 3. Now, if you use trigonometry and you find out the size of that trigonal void size, and you compare with the size of the sphere which makes up that trigonal void, then the radius ratio by trigonometry has been calculated as 0.155 for trigonal void. Again, the small r stands for radius of a sphere which exactly fits into the void, and capital R stands for radius of the sphere which makes up that void. So, if you want to see, this is what is small r and this is nothing but your capital R. Trigonal void. Tetrahedral void. Now, if you see, this type of packing was present in ABAB packing and also in ABCA packing. That means, this void that we are trying to say, tetrahedral void that we are trying to say, is present in both the type of packing ABAB, ABCA. ABAB, if you remember, was responsible for HCP and ABCA was responsible for CCP or FCC. That means, the void present in ABAB and the void present in ABCA are of the same type. They are tetrahedral void and octahedral void. Now, what is a tetrahedral void? If you check, if this is taken as sphere number 1, sphere number 2 and this is taken as sphere number 3, then are you able to see this dotted which I am trying to show is a sphere below. So, a void present between this 4 sphere is nothing but called as tetrahedral void. Now, if you see an octahedral void, this one, if I am shading it, then are you able to see as if there is a therefore which is seen here, therefore. Now, if you see below, right, there are 3 spheres which I am shading it in different manner below exactly. The void present between them is called as octahedral void. So, void trapped between 4 sphere, tetrahedral void. A sphere, right, void trapped between 6 sphere is called as octahedral void. Point to be noted, tetrahedral void is present in both HCP as well as CCP or FCC. Tetrahedral void we like to see. Are you able to see 3 spheres? Above them there is a 4th sphere kept. Then the void which is trapped between this 4 sphere is nothing but called as tetrahedral void or tetrahedral hole. If you are able to see this diagram, 3 spheres which have been shown by blue colored balls, and above that the red colored ball is getting placed, but that void which is there is called as tetrahedral void. Now, how to imagine a tetrahedral void? Imagine these are the spheres. Imagine they are brought closer. Then whatever you are able to see, this is a carbon of a methane, can be considered as tetrahedral void. So, how to imagine a tetrahedral void? Imagine methane, imagine methane, and in methane imagine hydrogen as spheres. Actually hydrogen are small, but you imagine big spheres, and carbon as another sphere which is exactly fitted as tetrahedral void. Here carbon is a larger sphere, but you imagine carbon as a smaller sphere and hydrogen as a larger sphere. That means this carbon is like our tetrahedral void, and hydrogens, which are to be imagined as a bigger spheres, are nothing but the actual spheres making up the tetrahedral void. Because it has a figure like tetrahedral, the void got the name as tetrahedral void. Tetrahedral void. So that was about tetrahedral void. Now what is the coordination number of tetrahedral void? Coordination number of tetrahedral void will be 4. Why coordination number of tetrahedral void will be 4? Because it is surrounded by 4 spheres. So because it is surrounded by 4 spheres, its coordination number is 4. After tetrahedral void discussion, we like to understand what is the position of tetrahedral void. Now for that we have taken FCC unit cell. If you take FCC unit cell, you have to imagine this sphere. Now how a tetrahedral void is remembered? They are remembered like as if you are having a therefore like 3 spheres. Above that you are trying to sphere it, put the 4th sphere. Or you can remember it as since like 3 spheres, and above that you are trying to sphere it, put the 4th sphere, then whatever the void is trapped is called as tetrahedral void. Now imagine this is like a therefore. This is like a therefore. Are you understanding? Sphere number 1, sphere number 2, sphere number 3, and this sphere which will be placed on this 3 spheres, this sphere which will be placed on this 3 spheres, then the space empty is called as which void? Tetrahedral void. It's called as tetrahedral void. Better imagination is from here to here. If you plot a line, then it is called as body diagonal. This is body diagonal. On that body diagonal, this is body center. This is body center. I will write on BC, and this is your sphere. Between body center and the sphere, the void that you will get will be called as tetrahedral void. So tetrahedral void is like this. Now if you see sphere number 1 is face center, if you sphere number 3 is face center, if you see this sphere which is also a face center, 4th sphere. So 3 face centers and 1 corner, the space trapped between them is called as tetrahedral void. So that tetrahedral void has been shown here. This is sphere number 1 which was a face center, this is space sphere number 3 which was face center, this is sphere number 4 which is also space center, and this is corner. You have to imagine sphere number 1, sphere number 2 and sphere number 3 are actually making a therefore, and sphere number 4 is placed over those 3 spheres. Then whatever empty space that you will get will be called as tetrahedral void. If I want to say if this is a body diagonal, this is a body center, and this is one of the corner, then here is a tetrahedral void. So tetrahedral void is a center of body center and corner. Similarly, if there is a tetrahedral void on this side, then there is a corner here also. So between body center and corner, the space empty is called as which void? Tetrahedral void. That means body diagonal, one body diagonal will have 2 tetrahedral voids. So it is a void surrounded by 4 spheres, therefore coordination number is 4. So again, for you to know, tetrahedral void coordination number is 4. Summary of tetrahedral void: it is a void surrounded by 4 spheres, therefore coordination number is 4. If you see, there is a red color ball which has been shown, that is nothing but a sphere which is exactly fitting into a tetrahedral void. These voids are located in FCC near every corner, and if you move from corner along body diagonal, we will find this body diagonal at the distance of the corner. So if you want to know, remember this is a corner, this is a corner, this is the body center, then there is a tetrahedral void here and the tetrahedral void here. So almost at 1/4 space the tetrahedral void is present, 1/4 space of body diagonal, that is A root 3. So, if you want to know what is this spacing, it is A root 3 by 4. That is a place where tetrahedral void is present. So, if you try calculating here, it is also A root 3 by 4. So, it is at 1/4 distance from the corner, and we know body diagonal is A root 3. So, it is surrounded by spheres, right, one corner and three faces. That is what is an identity of a tetrahedral void. Are you able to see this diagram? Tells you so many red colored spheres are tetrahedral void. So, if you take any body diagonal, then you will find the two tetrahedral voids. Now, any sphere has how many body diagonal? Not any sphere, any cube has how many body diagonals? It has 4 body diagonal, and every body diagonal has 2 tetrahedral voids. So, therefore, 4 body diagonals making up cube will have how many tetrahedral voids? 8 tetrahedral voids. So, any FCC unit cell will be made up of 8 tetrahedral voids. Are you able to see the diagram here? If you check, this is nothing but a body diagonal, and this red color dots are nothing but tetrahedral voids. If you see, right, if you go on plotting all this, you should get tetrahedral voids. They are not coming exactly, but they are tetrahedral voids. Every body diagonal has 2 tetrahedral voids. If you remember, this is the corner, this is the face center, this is also face center, this is also face center, and this orange color dot is nothing but tetrahedral void. By using trigonometry, we have found out a radius ratio of tetrahedral void is 0.225. 0.225, and there are how many tetrahedral voids? 8, and all of them are present inside the unit cell, and they are not shared by any other unit cell. Therefore, number of tetrahedral voids in FCC or CCP unit cell are 8. If you try to understand calculation of number of tetrahedral voids, FCC or CCP is made up of 4 spheres or 4 metallic atoms. Number of tetrahedral voids are 8. That means number of tetrahedral voids are double of number of spheres. So, number of tetrahedral voids are 2 times of number of spheres. If you see HCP, rank is 6, number of tetrahedral voids will be 12. You remember tetrahedral void is present in both FCC and HCP because they have similar type of packing. So, there are 2 tetrahedral voids per sphere. So, we will stop here only. In the next session, we will continue with octahedral voids. Set of void, octahedral void. Now, this octahedral void along with tetrahedral void is present in AB packing and ABCA packing. If you want to know again, AB packing is responsible for hexagonal closed packing HCP, ABCA packing is responsible for CCP or FCC. You want to see an octahedral void? It has been labeled as O. So, all those which has been labeled as O are called as octahedral void. Now, if you pick up any octahedral void, then imagine the sphere which are present below, which has been shown by shaded or lighter red color lines. If you check this, then they appear like sins, and above that, if you try to get this which is appearing like therefore, then whatever is void trapped is called as octahedral void. So, we remember as if there is a lower layer of therefore and upper layer of since, then whatever void is trapped is called as octahedral void. Position of an octahedral void, or more information about octahedral void we like to understand. Octahedral void, are you able to see? The 3 spheres with a blue colored ball are making the lower layer. This is lower layer, and the red colored sphere make up upper layer, and between them whatever is trapped is called as octahedral void. So, here you are able to clearly observe the octahedral void also called as octahedral hole. How to imagine octahedral void? Imagine SF6, sulfur, fluorine, 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 fluorine and fluorine. Although fluorine are smaller atom, in this case imagine fluorine as larger spheres. And although sulfur is a larger atom, imagine it is a smaller sphere, and that small sphere is nothing but our octahedral void. So, you should know the things trapped here in this space. This void is nothing but octahedral void. So, you should imagine in SF6 sulfur is your octahedral void and 6 fluorine are your spheres which are trapping that octahedral void. So, this is how right will be there. This is octahedral void. Although here green spheres are looking small, remember these spheres are much larger than octahedral void. So, that was information about octahedral void. It is trapped between 6 spheres, therefore, its coordination number is 6. It is trapped between 6 spheres, coordination number is 6. If you want to recall, trigonal void coordination number was 3, tetrahedral void coordination number was 4, octahedral void coordination number is 6. More about octahedral void. It is surrounded by 6 spheres, coordination number is 6. This is how it looks as a diagram, colored diagram, octahedral void. Now, octahedral voids, where are they present? They are present at 2 locations. Which are those 2 locations? We like to see in FCC or CCP. This is what is your octahedral void. So, it is trapped between the sphere 1, sphere 2, sphere 3, sphere 4, sphere 5 and sphere 6. If you closely observe, this is nothing but your body center. So, remember in FCC, your body center is an empty space and that is your octahedral void. If you check here also, this is what is your octahedral void, trapped between the 6 spheres. Here also it is trapped between the 6 spheres. So, octahedral void here trapped between 6 spheres and octahedral void trapped between 6 spheres. What is this position? If you check, it is nothing but edge center. So, where is octahedral void present? It is present at body center and is also present at edge center. So, alright, our query is, where is octahedral void? Our answer is, it is at body center and edge center of FCC, surrounded by 6 spheres, coordination number is 6. In FCC, there are 2 locations for octahedral void and it is at body center and it is at edge center. Okay. In body center, all face centered spheres are responsible for touching this void. At edge center, the void is surrounded by 2 corners and 4 face centered spheres. If you want, you can check. This is nothing but octahedral void, which is an edge center, right? All red color spheres that you are able to see, all red color sphere. If I number it 1, 2, 3, 4, 5, 6, all these are edge centers and edge centers are surrounded by corner A and B and are surrounded by 1, 2, 3, 4 are face centers, 4 face centers and 2 corners for edge center octahedral void. So, the void at the edge center will not be completely inside 1 unit cell, it is actually shared by 4 unit cell. Any edge center is shared by 4 unit cell. Body center is also an octahedral void and we know body center is present inside the sphere and is not shared by anyone. Void at the body center will be completely inside and therefore not shared by anyone. Again, our question is, where is octahedral void? It is at body center and edge center. Body center is not shared with any unit cell and edge center is shared by 4 unit cell. So, how to count number of octahedral voids? The counting is like this, right? You should know 12 voids are present at 12 edges with a contribution of 1/4 because they are shared by 4 unit cell. One sphere is at center. That one sphere, or we say body center, which we call it as void only. Void is present, and what is its contribution? Its contribution is 1. So, here the word should be void. So, one void at the center. So, total if you calculate, there are 4 octahedral void in one unit cell of FCC or CCP. So, if you try to calculate rank of FCC 4, that means it is made up of 4 apparent spheres. And how many octahedral voids we have calculated just now? Right, number of octahedral void is also 4. So, how many octahedral voids are present per sphere? There are 1 octahedral void present per sphere. If you go back, there were 2 tetrahedral voids per sphere, and now we have realized 1 octahedral void per sphere. This is what you understand. Remember, FCC is made up of 2 types of voids, tetrahedral voids and octahedral voids, and 2 tetrahedral voids are present per sphere, 1 octahedral void is present per sphere. FCC is made up of how many spheres? 4. So, total number of tetrahedral voids are 8, total number of octahedral voids are 4, total number of voids are 12. So, total number of voids are 3 times Z. Total number of voids is 3 times Z. So, for HCP if you calculate, we know FCC and HCP are similar in their packing with same packing efficiency of 74%. If Z ka value is 6, that's rank is 6, number of octahedral voids in HCP will be also 6. So, that was about octahedral void. More about octahedral void. Octahedral void is present at edge center. So, if you calculate radius ratio, this is how you can calculate. This is right octahedral void, this is lattice point for a spheres. So, if you calculate, what you will get? Actually, if you calculate, this is nothing but 2r, this is also small 2r, diameter 2r, this is capital 2r. That means, if you calculate, it is 4r. No, I have done an error. Error is like this. From this, there is only 1 r. From this, there is only 1 r. So, that means r plus 2 r. This is r, r, this is r, this is 2 r as a diameter, and this r. So, r plus 2 r plus r is nothing but edge length. That means 2 r plus 2 r is equal to a. That means r plus small r is equal to a by 2. So, this is what is the relation for octahedral void, and we know a is nothing but what? A is nothing but not a, 4r is equal to a root 2. If you substitute that value, 4r is equal to a root 2 for FCC, and we solve, then r by r will be 0.414, will be 0.414. If you want to see it again, then this is one sphere, this is your octahedral void, this is your another sphere. This is what it is. So, this is nothing but capital R's, this is nothing but capital R, this is nothing but 2r. That means r plus 2r plus r is equal to a edge length. So, 2r, r and r, 2r will be equal plus 2r will be equal to a. So, r plus small r will be a root a by 2, and we know there is a relation that 4r is equal to a root 2. If you substitute all these things and you do trigonometric calculations, then radius ratio will be 0.414. If you remember that small r is nothing but the radius of the sphere which exactly fits into octahedral void, and the capital R is nothing but radius of the exact sphere makes up that void is 0.414. If you want to summarize, then there is a small numerical by which we can understand. Compound is formed by 2 elements M and N. Element N forms CCP and atoms of M occupy 1/3 of tetrahedral void. What is the formula of the compound? Then how you do that calculation? The calculations are like this: N forms CCP. If N forms CCP, it will be 4. Then M occupy 1/3 tetrahedral void. if it occupies 1/3 tetrahedral voids, how many tetrahedral voids are there? 8. So how many m will be there? 1/3 of 8, 8 by 3. Hence formula will be m will be 8 by 3, n will be 4. So it will be m 8 by 3 n 4. If you simplify and you do the calculation, then you will get 2 m 2 and n 3. First you multiply by 3. If you multiply by 3, you will get what? M 8, 4 multiplied by 3. Divide both the things by 4, you will get m 2 and 3. So formula will be m 2 and 3. This is how numericals of voids are done. If you want to see again, n forms CCP, therefore it is 4 n number. M occupies 1/3 tetrahedral voids. Tetrahedral voids are 8. 1/3 of tetrahedral voids is 8 by 3. So m is 8 by 3, n is 4. So if you write down and you simplify, the formula will be m 2 and 3. Cubic void, if you would like to see, cubic void, if you like to see, it is present right inside this empty space. This empty space is nothing but your cubic void. You can imagine cubic void like a body center, but you should know it is SCC, and the space empty inside is nothing but cubic void. And you can imagine cubic void like BCC. Only thing is the body center is your void. Void means empty space. It is surrounded by 8 spheres, therefore coordination number of cubic void is 8. That is the highest coordination number of the void. Radius ratio, if you calculate by using a proper trigonometry, then the radius ratio will give you r by capital R as 0.732, where small r stands for radius of the cubic void, capital R stands for radius of the sphere which makes up cubic void, and 0.732, that is the largest value for any void around. The void is completely inside the unit cell and is not shared by any other unit cells. So number of spheres making SCC, that is rank, is 1, and number of cubic void is also 1. So how many cubic voids are present per sphere? Number of cubic voids present per sphere is 1. So what is the position of cubic void? Cubic void is at body center of SCC. That's 1. Then how many cubic voids are present per sphere? Answer is 1. For simple SCC, how many spheres make up SCC unit cell? 1. How many cubic voids are present? 1. So number of cubic voids per sphere is 1. Summary for all. Trigonal void, the value was 0.155 times of R. Tetrahedral void was 0.225 of R. Octahedral void is 0.414 of R. Cubic void is 0.732 R. So we can clearly understand the smallest is trigonal void and largest is cubic void. Number of tetrahedral void per sphere is 2. Number of octahedral void per sphere is 1. Number of cubic void per sphere is 1. You should know tetrahedral void and octahedral voids are present in ABAB or ABCA packing. That means they are present in HCP and FCC, while cubic void is present in SCC, that means present in AAA type of a packing, while trigonal void is commonly found void right everywhere, commonly found void everywhere. So that was all about voids to understand. So we come to the end of the entire void and void related discussion. Thank you.